Hi, and welcome in the second part of reversing one of the Hitcon 2019 challenge called core dump. If you haven't watched the first video, I encourage you to do. In the first one, we dealt with the core dump file, and we finished with extracting parts that were called in the main part of the challenge. So that was where we left off. So now we'll pick up and we'll try to analyze the parts. So I already have parts imported. I left one of them missing just to show you how it's been actually done. So the parts are just pure binary. So there is no language pre-selected by Ghidra. So we'll have to do it ourselves, and we know it's 64-bit. So I'll just filter by that, and it's in probably GCC. So we will use that. Okay, so we have all the parts imported. So now we'll start analyzing them one by one. And yeah, so again, we start with analyzing the binary. Ghidra recognized that, okay, we have one function. Actually here it's just this one function, because as I said, this is just pure function, pure code that's being called from the main assembly. So there is nothing fancy here, just pure data. And the first one we can try to well, actually there's no string. What I wanted to show decompiled, so we can rename standard just to have a bit more clear, part 0. And we knew from the calling code that actually those are not, the first one is not long, the second one is int, and it's like a len of the flag being passed, and this one is like a char pointer to parts of the flag that being passed. And if you remember, if not, you can check it in the first. I think there was like 10 characters being passed to this method. So we can rename it to char pointer, well, not rename, but change the type, and we can call this flag, so we'll know whenever it's being used. And we can already see something here that looks suspicious. There are some byte values that kind of look like ASCII, so we can go to our listing here and just convert it to ASCII and see. And actually, yeah, it's a string dump, which is also part of the name of the challenge. And we can also see some strangely looking characters here, and we can also convert them to some char sequence and char sequence here. And if we counted them before they actually being converted to decimal, there were 10 characters here. So it's probably part of the encrypted data, or part of the flag that will be compared after some kind of decryption with what we passed here, and based on that we'll get a result whether this part passes or not. But since we know it's like a part of the flag, and we knew that we had 10 characters passed here, so we can also change type of this to char and have 10 characters in it. And now we see this strange pattern that Ghidra uses, but at least yeah, we get the this is something we can we know that it's like a 10 characters array, and we can also rename it to probably encrypted flag. Okay. Again, we see a while and parameter being used. We can rename it to I, so it will be our counter in the loop. And yeah, let's just focus on what's actually going on in this loop. So okay, we have some kind of I being converted. Well, we can leave it for now, but what's happening here? So we take the character from the flag, so from this one we use this local 48, which is this, if we remember correctly, this was this dump, and we use XOR on it. So for sure, this is our key. And also, I think I didn't change the type of the key. We can also change the type to be char for characters. And yeah, now Ghidra converted to this nice array indexing. And here, this notation is just getting every byte from this key based on the I value. So basically based on the loop counter. And there's one trick here. This is -7, and actually with this notation it might be tricky what actually is being done here, whether we are XORing flag character with a key character and then subtracting 7, or we are XORing key character -7 with a flag. And we can find out by actually analyzing the code here. We should find the 7 here. So, okay, so we are subtracting 7 here and then we XOR. So in this one, AX is part of the flag. So we subtracting 7 from, not part of the flag, but part of the key. So we subtracting 7 from the key and then we XOR it with a flag. So maybe there should be some parentheses around that, or maybe the order of execution tells us that, but I never know. So for me, it would be easier to have a parenthesis that would tell me what's going on. Okay, and what's this actual, this local? Local is some kind of, local variable where we store the values. So we could also change its type to character, well, I guess it has to be 10. And again, Ghidra resolved it nicely to this array notation, and we can rename it to something more meaningful, which could be, I don't know, potential flag or whatever it is. And we iterate one by one after we are done with all the characters. And at the later, when we do that, we see a similar loop, but this time we check if our potential flag, which we just generated here, is equal to this encrypted flag, which is this those oddly looking characters. So yeah, this is just like we take the flag, we encrypt it with the key dumb, and we see if we get whatever is here. So it's just a basic XOR with a small twist with this -7, which well, doesn't make it that hard, but at least we need to be sure we include it in our algorithm. And we could do it manually. There's just 10 characters, but yeah, we don't have to. Actually, I have part 0 Python script. So we have the data, we have the key, and we have this -7 in the subtraction from the key characters. We zip it and we generate the flag, because XOR is reversible with the same operator, so we can extract the flag by doing the same operation on the data that we expect to get. Okay, and if we run the part 0, Python will get the first 10 characters. So thank you. So we get the first 10 characters of the flag. And yeah, part 0 was quite easy. Let's look at part 1 and what we can find there. Okay, we'll just again start with analyzing, just one function, the same, a lot of local variables. So here, if we just scroll, it's a bit more than before. There's for sure more code. We have just one parameter being passed, but we know, okay, it's not long, it's a char pointer. We can change the type and we can rename it to flag. So that's one. Also, we can see some constants being used here. We don't know what actually it is for, but we will find out when we analyze it. But maybe for now, let's focus on something simple. So again, while, let's rename it to I. We'll have one local variable out of the way. And the while is a bit longer than before, but we can still see some XORs, some locals variables here and there, and locals actually here it's, yeah, this one is a flag, it's from the flag, and this one is also from the flag. So we can change it to character, and this could also be character, but let's like, yeah, very good naming, character 2, or maybe we'll just call it A and B, A and B, but they are from the flag and they are limited to 255. Okay, so we have one while, but we can also have another one inside, and again, yeah, while we can just rename it to J. And okay, and we have some also like an array here where we put some values. There are ASCII range. We could actually check what are the values, but I'm not sure if they will tell us something. So it's C, O, it's probably core. So we had dump in the other one, and this one is core. Okay, yeah. Okay, so I guess we are on a good track. And then, okay, so we are doing something with those characters, and they are used, A and B are used in this one, and the same B and A. So basically they are cross-referenced. So A uses B and B uses A. So it's for sure a bit more complex algorithm than before, but nonetheless, yeah, this is something probably we can deal. Okay, and we have those locals, so let's just call it some kind of temp array. And so we have 4 elements in the temp array. We have this local variable which we don't know, but it looks like, okay, we add something, then we increase by this lead dead, and then use it for the B. Okay, this is some kind also like temporary, I would say, variable that's being used, but it's also being used here as an indexer in this temp array. So let's call it like IDX. It doesn't really matter, it just, we want to simplify. Of course, if we understand what's the purpose of particular variable, we can rename it later. But for now, let's just call like that. Okay, so the loop is a bit shorter. We probably could try to think what is the algorithm here, but let's focus on this one. So in this one, we have, after this loop, we trans like 32 times. We do it 4 times. So 4 times we iterating, and then in each iteration we run 32 times. We compare the A that we generate after this 32 runs and B with some local 38. And if we scroll back, the local 38 actually has those values that we identify at the beginning. So, and we comparing, and then if it's not equal, we set some variables to 0, and also this variable later it's passed to this uvar1 and it's being returned. So actually this is a result, and yeah, this is also like a result with underscore. So this is what we are returning, and here it just, we are comparing whether we are equal. So whatever flag we pass here, after each round, each of 4 rounds we do here, we should be equal to the values in those locals 38. So this, and this depends on the round. So we can rename it to some kind of final values that we expect to have. And yeah, it's basically based on the index. So I being 0, then it will be 0 and 1, and 1 would be 2 and 3, and so on and so on. And we compare A and B's. And now how we could find out what's this algorithm? We could actually, there's 2 approaches. We could not find out what this algorithm is. We could just write it in C or Python, and that would be fine. But also we could try to find what it is. And actually here it's a bit more difficult to find out the algorithm because they change the constants. Either it's like their algorithm, but usually, yeah, people don't invent their own algorithm. This is probably something standard, but if you haven't seen it before, it might be tricky to find out what it is. But here are some pretty unique constants, I would say. Well, probably will nothing get by this constants. Maybe we'll get some write-ups from Hitcon. But those 4s, 5s, and those logical operators might give us something. But also it comes with an experience that you already seen this algorithm with the correct constants, and then by just Googling the constants, you could find out what this algorithm is. And in this case, this algorithm is this XT algorithm. I think that's the one. And if we scroll down, we could see the same more or less operation that we see in Ghidra. So it might help. You also don't have to know it because, yeah, as I said, you can just type it exactly like this in Python or C++ and get the yeah, try to crack what's the flag actually will give us the results. But I can see I can still have some values here, and I think it's due to the problem that actually Ghidra wrongly identified this final being 5 characters, because I think this should have not 5 elements, but it should have 8 elements, so we can always change it. And now, yeah, now it's a bit clearer that we have 8 values that we use, and yeah, we run the algorithm, this cross calculation of A and B's, and then we compare with the final values. And yeah, we could do the same in C++. So as I said, the task was done with disconnected during the competition, so I guess that's more or less his work. I tweaked this a little bit, but more or less it's just a brute force. So you run through all A's and all B's, and you find out what A and B's matches with those expected values in code that we saw in Ghidra. So let's just run part 1 and let's see what we will get. So we got some A and B's, and they should be read like first A's then B's. So the first flag was thank you so, and then there's underscore match underscore F0. So yeah, we got 2 parts of the flag. So let's just dive into the third, but part 2 of the of this challenge. So let's just switch again back to Ghidra. Let's go to part 2. Again, nothing was analyzed yet. So Ghidra will analyze, will find the function we can jump into, and we can rename part 2. And here again we have like a byte parameter and int. So this is len, we can rename it, and this is flag that we are passing. And again, there's a bit more here and also more code, but nonetheless, I guess we'll find out. So again, bunch of numbers. We could start with those. We could go to this listing and try to convert, see if it's anything readable. But we can see there are some characters, but it's probably nothing that we can read. So we don't have to do it because for some reason Ghidra changes to decimal values here when we use the char sequence, and I prefer to have unsigned hex. So let's just go back to unsigned hex and let's just try to focus on analyzing. So how many of those we have? We have 2, 4, 6, 8. So probably this is an array. So there is no 8 separate local variables. It's an array. So we can try to convert to array of 8 values. And yeah, probably that was not the best idea, because something I lost all the values. Okay, local 58. We have local here and local here. So yeah. So what the type should be? Let's just convert it to char pointer for now. And it's no, it should not be like. Okay, so let's just maybe back up a little bit and see what's being done here. It's usually helped to convert those types, but yeah, if something is not correct, we can always revert, and yeah, maybe later we'll know what's going on. We have our flag. It's being assigned to this local C8, so we can also rename to underscore flag to have a clear picture where it's being used, and we can see, okay, it's being used in this while, and yeah, so it's being used here and also in few other places. But what's going on here? So we take the first character of the flag, we add it to some local variables, and yeah, and assign it to this variable, and then we use it also here. Okay, and this is local 58 is this string. Okay, and here we use second character from the flag and the first one, and we do some bit operation on them, and what else? Okay, and we also again use this local 58, but local 58 is actually, it has to be some kind of array, because we use it as a pointer and then we add a value to it. So it is more or less like accessing a pointer, well, yeah, accessing array element. So it has to be array element. So let's just maybe, okay, convert for now to char pointer. Okay, we lost some of those values, but okay, nonetheless, for now it's fine. And it's being converted to, okay, local. Okay, what is else going on here? And we also have those values, and those are used here. Okay, so those are our finals. So this is final value. So this one we will be comparing. And local 98, what is local 98? This is, okay, so this is also an array, but we don't know what size. Okay, maybe that's the problem, because I didn't specify the size, so it doesn't know, okay, how many values it should put. Okay, so let's just back up a little bit. Thank God we can okay, so how many values I have here? So it's like, this is 8 bytes, and we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's like 64 characters. So now let's convert it to char 64. Okay, now it's a bit better. Okay, so now we know we have all those values, and here we have 8 also, and times 3 at most, so it will be char 24. Okay, so we have those values. Yeah, and now Ghidra identifies correctly that this value is used as an index in this array. So this is some kind array we will just name in a moment. And we use local 8, which was this flag. Okay, I reverted the renaming, so let's just call it flag, and now it's a bit more clearer. So so this is, how do we call it? This is some kind of lookup buffer. So we have lookup buffer with some values, and based on the flag, we take a value from this lookup and we assign to this local D0, which is local 98, which is also, I guess 8. So I guess it's also 64. Yeah. And we assigned it. Okay, so now it's even clearer. So let's just give it, this is encrypted flag. So this is basically what we will be doing here. So Based on the lookup and on the based on the flag, we take from the lookup the character and put it as a 0 character in this encrypted flag. Then the first character in the encrypted flag is based on the second character in the flag and the first one, or like at index 0, with some bit manipulation. Then we move this encrypted flag by 3, but I'm not sure if this should be here. It should be more or less at the very end, but nonetheless. So the second character in the encrypted flag is based on the third and the second characters, again with some bit manipulation. And then the, yeah, so this is here. So this is like a fourth character in this encrypted flag is based on the fourth character of the flag. Is that correct? So it's, yeah, I think it's correct. So basically we are doing some kind of bit manipulations on the flag bytes. Each time we process how many? 1, 2, 3 characters of the flag, and we produce 4 characters of the encrypted flag. Yeah, and we do it until we reach the end of the flag. So yeah, some kind of encryption going on, and later, yeah, I guess again. So this is like 24th. We'll get 24 characters. This is our loop counter, and local 98. Where do we have local 98? So local 98 is our encrypted flag. Okay, we can also give it a name, encrypted flag with underscore, and local B8. What's local B8? Local B8 is this one. So this is our final state that we want to reach. So, okay, final state we identified. We have encrypted flag, and again, this is a result. So we rename it as such, and again, this is like some kind of conversion to oolong, and we return it. But I guess result, what's the type of result? If we would, yeah, it's uint, this is oolong, we could just, I guess, probably convert one to the other. Okay, and again, this algorithm, probably we could look it up, maybe it has some name, but also it's not that difficult to brute force. Each time we process 3 characters of the flag, so, and produce 4, and we want to get this final state, so we can reverse it. We can get the final state, go over each 3 letters in combination and see if we will get that result based on the lookup table. And basically this is what's done in part 2 Python. So we have those values, I call them A here. So this is lookup is A, we have finals, and we just have find characters. So we use again itertools product with printable characters. Well, I can see I have this alphabet which I didn't even use. Well, printable is, I guess, more cases, but let's see with the printable. I think it will be fast anyway. And we have those checks. So basically we generate first characters, we compare it with the character at index 0, what we should expect. If it's different, we'll just go to the next triple, and so on with the second, third, and final fourth character of the encrypted flag. And then at the end, we'll just join them and return. And we do it for all the finals, which we have 24th. So I guess from 24th, we'll get, yeah, how many characters? 18 or something like that of the flag in return. Yeah, so it's also fairly easy. I mean, like if you understand the algorithm, what's going on, and I guess part of it is just simplifying the code, because with those locals and not understanding what actually each character means, it might be difficult, but if we rename them to something more meaningful, it makes more sense. Also with this array notation that gives us an idea, okay, here we access some kind of index of an array based on the flag, which, yeah, makes sense. Okay, so let's just run part 2. And it will give us, yeah, so we had thank you so, much for recovering the, well, we already know probably what will be later, but let's go further and see what actually interesting things are being there. Okay, so we have part 3. Again, analyze, standard settings, we go to the function, we change the name if we want to. Of course, during the competition, no one changes the name because it doesn't make sense to do that. Sometimes changing the type makes sense because you want to analyze, so we know that this is not a long, it's char pointer, and this is like a flag, at least part of the flag, and this is its length. Okay, again, there's some local variables created, and again, we need to analyze. We have some while. Again, if you see while, just change it. Maybe it's not the best because we are like going down here, so maybe let's just use count instead. So it's basically this one clears this buffer, local 478, which is 126 characters. So this is like a buffer. We can rename it already, and probably we can change the type to char 126. So this is our buffer. So we'll be doing something with this buffer. We don't need to change it more. It's quite clear. We have some values here. Let's see if there are anything readable. Okay, there are. Please don't crack. Okay, please don't crack it. Crash in this, probably crash in this function. Okay, so we have some message from authors, and there's some more characters. Okay, we'll try not to crash, but again, we could change the type, so it's like 8, 16, 24, it's 4 times 8, 32, so it's like 44 characters. We could change the type of this, so it's like char, how many was it? Like 36. I will give it for now. Should be fine. Yeah, it's probably enough, 34, but okay. So it's like a message. We don't know what it is, but at least it gives us some matches. There's more some values here we could also convert. Okay, we can see it's nothing readable, so let's just keep it as it is. And now, okay, we have a while loop again. Rename the variable to I, so it's a bit more clear. And yeah, so we set a value I on the I element of the buffer, and that might already raise a flag if you already seen a lot of encryption algorithms. But let's continue. So after this while, we have another while which also is to this f6 value, and then okay, we use the message of I divided a reminder of 22, so I guess it's 22 hexadecimal characters in this message, and we take the buff of I element with some local, we don't know what it is, but I guess it's some kind of temp variable, and also we take the I element from the buffer to this variable, and then okay, I know it might be a bit fast analysis, but if you look closer, we just more or less exchanging characters. So we take buff plus I to this variable, and then we put it to buff plus temp, and at buff plus I, which was used here, we use this buff plus temp. So basically, okay, it's not a temp, it's some kind of index. We can rename it. This is like an index value, and this is a value. Okay, so at buff plus I, we put buff plus index, which is this value, and at buff plus index, we put the value which was before at buff plus I. And again, you could search for it, but yeah, it's basically RC4, a bit modified to make it a bit harder, because in RC4, it's not to F6 we calculate, it's actually to 255. So it's a bit more values we generate. So this is like this S-box generation, and this is like a part of the exchange, and this is the actual encryption. We could do a bit more renaming, but this is basically an RC4. And again, it comes with a bit of experience. I'm not saying I'm super experienced, but if you see RC4, it's quite obvious this is RC4 with this slightly modified value, and this message is actually being used as a key to RC4. And the problem with this part is that this is not a standard RC4, so you have to find the components of RC4 and use them in your own script, and you cannot use the RC4 pre existing version. You have to modify it to use this constants. As we can see, it's used everywhere, and in original algorithm it's 255, I think. And yeah, at the end we'll have a comparison. So this is what we generate. I guess this is what is being compared to, and this is this string. We could change the type, change the name to final, and the type would be, I guess, how many? It's 8 plus 9, 10, 11, I guess 12 characters we have, so we could use it char12 to have it a bit more clearer. And yeah, Ghidra will give us this nice notation, but once we know it's RC4 modified, we can again write our script to just decrypt it. So we have our key. Please don't crash in this function. We have our final value. I'm just printing it, and we have those two functions that are based on RC4 is based. One is this key scheduling algorithm with modified count, and the other one is this pseudo-random generator algorithm. And the RC4 is just use the key scheduling to generate this S-box, and use S-box in this pseudo-random generation algorithm. And RC4 is just basically just generate the random values and just XOR it with those values that RC4 gives you. And that's all. So we can run it, and it will give us another part of the flag. So thank you so much for recovering the flag. I love YO, probably you. But let's jump into the last part of this challenge. So part 4 ahead of us. Again, let's just open in Ghidra. Again, let it analyze. Okay, and yeah, just one function, one parameter, and actually quite short. Okay, let's just change the type to char pointer, and param1 instead, let's call it a flag. And we already see, okay, while flag of local 24, so we know how to name this variable, is not equal to null character. We just assign to this ivar I plus 1. We take the I character and XOR it with this local variable. So let's just call it like a temp variable. So we start with -1, we XOR. We have 7 here, local, and -1 less than local 20. And we do some kind of magic here with bits. So we have this temp, and we move it to the right, and then we end it with 1 and some constant value. And actually, if we look for this constant, we'll get that this is something that looks similar to CRC for 1 byte. So it looks like we are some kind of calculating CRC here. with 1 byte. And maybe we could use CRC algorithm to find out the values, like already existing CRC, but also this algorithm is not that difficult to actually write it down ourselves. So we have a flag, we just do some calculation and we expect the value of temp to be at the end to this. So we can just simulate this in Python and recover the bytes. And this is what actually being done. So I have the code here just to look at it while coding, and we have a brute force. We have some kind of alphabet here. And I think the number of characters was known from the main script, that we knew that it's only 4 characters we are passing here. So also it's not that big because we know that there are 4 characters. If it would be like, I don't know, 16, it would be too difficult to check all the combinations. But since it's not that big, yeah, we can do it. So here it's like ASCII lowercase, uppercase, digits, and some punctuation characters. It's usually, when I do such brute forcing, I usually start with like ASCII lowercase, uppercase, and digits, and if it doesn't work, I sometimes add some special characters until it works. If it doesn't work, then I switch to printable, but in printable there's a lot of other stuff that might not be needed to be checked. So yeah, I usually start with a smaller alphabet and then increase it if it doesn't produce any results. But in this case, yeah, this is enough, and we will get the final part of the flag. And part 4 will give us, it takes some time. In comparison to the other one, this actually takes some time, but still I think we'll manage to get it today. So let's just wait a little bit, and I will try to amuse you while we are waiting. I guess it might be a bit slower due to all the recording that's happening, and I hope it will at least produce a flag. But let's see. Yeah, and as I mentioned, this is some kind of like, if we Google this constant, it gives some algorithms that calculate CRC for 1 byte, but it's not the actual CRC32 for the data. So it's not that we could take those 4 characters, calculate CRC on those 4 characters, and it will be equal to this value. It will not match. So basically there's a bit of modification. And I guess it's also what the challenge authors wanted. So they wanted to have some kind of known algorithms, but they wanted to tweak it a little bit so people cannot just use existing tools. They have to modify a little bit, or at least write their own scripts to find the flag. And we got U underscore and a heart symbol. So that's all 5 parts of this challenge. So this is how we could get the flag. Of course, during competition, some of those things you don't have to do because you want to get the flag as soon as possible. But when we are learning Ghidra or learning reverse engineering, we can do a little bit more. Just to play with the tool and find out what we can do with it. Okay, so I guess that's all the 5 parts. I hope you like it, and if so, please like the video and subscribe the channel, and see you on the next challenge. Bye bye.